Hi there, I'm Nix, and this is part 2 of solving the duplicate zeros problem, where I focus on creating a more optimal solution in terms of time and space complexity than the previous 2 solutions that were in the last episode. As always, going to solve the problem in the C++ language and give you a detailed explanation of the entire process, from the planning stage of the algorithm to the code to the analysis of the time and space complexity, LeetCode, ranking, so on and so forth. If that sounds good to you, stay tuned. Welcome back. So let's briefly remind ourselves as to what this problem entails before we start planning out our method of attack for it. So we've got a fixed length array here. We have LeetCode name it a pirate sound. We duplicate each occurrence of 0, and we need to shift the remaining elements to the right. Note that elements beyond the length of the original array are not written. They're just chucked off into the pit of oblivion, never to be heard from again. And we also want to do this in place. Now, the goal of creating this algorithm is to optimize it by minimizing the time complexity and the space complexity. Now, as opposed to the algorithms that I created in the previous video, which if you haven't checked that out, I'll attempt to put a link off in the upper corner somewhere that you can easily use to check that out if you want to. But as opposed to those algorithms, we want to minimize the amount of time this algorithm takes and minimize the amount of space it takes as well. That essentially means that we can't use nested for loops, because that makes time complexities on the order of big O of n squared usually, and we want to do better than that. And we also need to do this strictly in place, which means to me, we can't use any additional containers. No making new array, vectors, stacks, queues, no nothing like that, because that requires extra space carved out in memory to create that additional container. Now, how do we do that? Well, let's take a look at this example array and start figuring out the logic that we're going to need to use to craft the algorithm. Bring up some nice graphics. Thank you, Mr. Whiteboard. And let's put the array on there. Now, in the algorithm that used the nested loops, as we iterate through this array, every single time we see a 0, we have to go to the end of the array, iterate backwards, and shift everything one place over to make room for the new duplicated 0. We start moving forward again, and again, once we see a 0, we have to move everything back again one place. So instead of using that combined nested loop algorithm, if we can run through the array once and get the necessary information we need out of that iteration, we can then have a second loop that takes that information and uses it to shift the values to their appropriate destination. In other words, instead of taking small little baby steps toward where the values start and where they end up, we want to go straight from point A to point B and cut out all of the side trips, the tourist traps, baby steps, all of that. So let's look at this array here. As I look through it, I see one 0 here, another 0 here, and I know these two zeros are eventually going to need to be duplicated. But when I see this 0 and I know that it's going to be duplicated, I know that whatever is at this position, I don't need to care about. Because whatever it is, if it's a non-zero or a 0, it's not going to matter, since it's going to be chucked off into the pit of oblivion anyway. It's not going to stay in the final array. So every time I see a 0, that means I have one less place at the end of the array that I need to care about. So once I reach 4 here, I've seen every number that's going to remain in the final array. And I also know how many zeros are going to be duplicated. Now check out this 4 here. With 2 zeros to be duplicated, this 4 is going to be moved 2 places to the right. When I reach this 0, it's also going to be moved 2 places to the right. And then the position to the left of it is going to be filled by a duplicate 0. Once I get to this 3 here, now my zeros that are left to be duplicated have been reduced to 1. This 3 is going to be shifted 1 place to the right. Same for the 2, same for the 0. So that means how far the numbers are shifted by is going to be equal to the number of zeros that are going to be duplicated. So this leaves us with a couple of points to keep in mind when we craft this array. We know that the count of the duplicate zeros is going to help us determine how much to shift the values. We know we're going to have one loop that is going to be used to count those zeros. And then we're going to have a separate loop that's going to handle the shifting and the duplicates with that information we've gathered from the first loop. Now that's the general gist of the algorithm, but to make sure that it's going to work in all test cases, we're going to have to delve a little bit deeper into how this works. We're going to do that with additional examples. We have now 2 arrays here, example 1 and example 2. We go through this first array and let's count the number of zeros that are going to be duplicated. We see this 0, which means we don't have to care what's in this place. That's 1. We see this 0, that means we don't have to care about this place. And at this point we've reached the final count. 2 zeros are going to be duplicated. Now let's contrast that with what we see in example 2 here. We go through the array. We see this 0 here, that's going to be 1 duplication. We see the second 0 here, and our count is currently 2. We go to the end here, and we see this 0. Now, this 0 is still going to be present in the array, there's still room for it, but it's not going to be duplicated. And this is what we have to distinguish. In both cases here, when we go into the second for loop, that is going to handle the shifts and the duplications, the value in the starting position is going to be a 0. And depending on the particular count and the array size, that 0 may or may not be duplicated. In example 1, it was, but in example 2, it was just shifted and wasn't duplicated. So in our second loop, if we just have code that says, hey, if you see a 0, shift it and duplicate it. That's either going to A, result in an out of bounds error, or B, give us the wrong answer depending on the specifics of the array's properties. So we need to be able to distinguish between whether this starting place 0 is going to be duplicated or whether it's just going to be shifted. How do we do that? Well, in this case, in example 1, the total amount of zeros that are going to be duplicated is going to be 2. And the total amount of zeros that are present in this array as it originally is also 2. Remember, we don't care about this last place. We never look at it. All we're concerned about is the values that are still going to be present in the modified array in some fashion. So here in this example, 2 zeros duplicated, 2 zeros present in the original array are going to remain. In example 2, however, we have 2 zeros that are going to be duplicated, but we have 3 total zeros in the original array that are still going to be present in the new array. That clues us in that this first loop that's going to be counting the zeros has to actually count 2 things. Count the zeros to duplicate and count the total original zeros that are still going to be present, and use those pieces of information in the second loop to do the shifts and duplications and make sure that it's going to handle any scenario that the test cases throw at it. With all that information, let's start the coding process. First up are the two variables to keep track of the count of the zeros that are going to be duplicated, and just a regular count of zeros that are going to remain in the array, as well as some comments here that I used when I was crafting the algorithm to begin with to keep track of my examples to myself. Next up is the for loop. This is going to be the one that handles the counting of those zeros. The thing I want to point out here is the condition where I is going to be less than array size minus count zeros to dupe. In other words, this condition is going to go until we reach the end of the array values that will still remain in the modified array. If count zeros to duplicate ends up being 0, there are no zeros in the array. Array size is going to be 1 higher than the final index, but since I is going to go until it's less than that, it will go until the end of the array and won't reach any out of bounds errors. For this condition in this example here, chugs along, finds a 0, count goes up to 1, and we're now going until it is less than the array size, in this case 9, minus 1, which is 8. We're going to less than that, which is 7. Index 7 is right here. We keep going along until we reach 0, and this condition is set up so we will be able to see and evaluate that final position that ends up still being present in the modified array. Next up is the if statement that is going to handle counting the zeros that are going to be duplicated. Now the first condition in it is fairly straightforward, if the value you're looking at is in fact a 0. But the second condition here, using this AND operator, is there to verify that there is still space enough present in the array to handle the duplication. If I is not equal to the array size minus 1 minus count zeros to duplicate. In this example here, we chug on through counting our zeros, and when we get into this 0 here at index equal to 6, array size minus 1 minus count, in this case, is going to be equal to 9 minus 1 minus the current count at this point. And remember here, we haven't yet counted this. So our current count so far at this point is 1. So 9 minus 1 minus 1, 9, 8, 7. That side would be equal to 7, but our index value at this position is equal to 6. So 6 is indeed not equal to 7. So this is going to register as a 0 to be counted, and a 0 is that's going to end up being duplicated. In this example here though, while we go through the array, okay, we have 1 0, 2 zeros, and when we get to here, what does this end up being evaluated as? Well, at this position, I is equal to 4, and at this point, the array size being 7 minus 1 minus the current count so far being 2, 7, 6, 5, 4. In this case, at the index we're currently at, 4, and array size minus 1 minus count zeros to dupe also being equal to 4, this is, oh, well, that's false. So this entire thing is false. We're going to end up being here, and it's going to recognize that this is not going to be a 0 that's going to be duplicated. So this condition is present to make sure space is essentially still available for it to be able to be duplicated. Next up is a separate if branch, because we don't want to put this in an else or an else if, because we want to have both of these if branches executing at the same time, as long as their conditions are met. We want to count the zeros to duplicate, and we want to also count the zeros total that are in the original array that are still going to be present. So in this case, as long as its value that we're looking at is a 0, you're going to count it. Now that this for loop that handles the counting is completed, time for the next for loop to come in. This is going to be the one that iterates in reverse and goes as long as this count zeros to dupe value is greater than 0. And we're going to start when I is equal to the last index in the array minus whatever the count is, ignoring the stuff that's not going to appear in the modified array. First up is the if condition that handles the scenario where you have a starting 0 and it's going to end up being duplicated. In this scenario, 3 conditions have to be true. The first, I has to be equal to the array size minus 1 minus count zeros to dupe, which means that I has to be equal to the starting place. Once the for loop executes more than once, I is going to decrement down, and this is no longer going to be true. So this makes sure that we're at the starting position. In addition, we also have to be looking at a 0, and finally, our count zeros has to be equal to count zeros to duplicate, because we know if that is true, we're dealing with the 0 that's going to be duplicated and not just shifted. Once all those 3 conditions are met, the code within the if branch executes and sets the array value that's equal to the position plus the shift count and sets that equal to 0. We also have the array value at the position plus the shift minus 1 being equal to 0. Once we handle the shift and the duplication, we then decrement the count zeros to dupe variable down by 1. This if branch handled the scenario where the starting 0 was duplicated. So this else if branch is going to handle the starting 0 by shifting it only. We're going to do that by looking to see if these 2 conditions are true. We're still at the starting position, and the value that we're looking at is still equal to 0. I could have a third condition here where the count zeros is not equal to count zeros to duplicate, but that's sort of redundant already since this branch is below this one. And if these 2 conditions are true, but this one is false, it won't go into this branch anyway, and it will go into here. Once those 2 conditions are proved to be true, all we have to do in this case is add the code line that handles the shifting and sets that equal to 0. We don't have to do the duplication, and because we're not at a 0 that was counted in the count zeros to duplicate variable, we don't need to decrement down that variable. Next up is the scenario which handles the non-zero values. In this case, if we are looking at something that does not have a value equal to 0, they just get shifted by their appropriate space. And we set whatever that position's value is to whatever the original was. The final situation to handle is when we're dealing with non-border zeros. So in this case, the code is exactly the same as it is up here. We want to set the shifted position to equal 0. We also want to set the shifted position minus 1's value equal to 0. And then since we've duplicated, we want to reduce our count to that by 1. And with that, we should have an algorithm that handles all the scenarios that the test cases should throw at us. And this should work. Now let's see if that's true. Run code. Pending, judging, finished. Is this answer that answer? Yes. Okay. Moment of truth. Submit. Pending, judging, accepted! Green text! Everything is sunshine and rainbows. Wonderful. Okay. So with that, let's officially start the final part of the video, the analysis section. Looking at this algorithm here, we indeed do not see any nested loops. We only see single loops here, which indicates that the time complexity, instead of being big O of n squared, like it was in a previous algorithm, we now have reduced it to a big O of n magnitude. In other words, linear time, which is a big improvement. In addition, we also see that other than creating some constant variables here that are in use, we created this algorithm that did not need to use any other containers except the original array that we're given, which means that we are going to deal with an algorithm that is constant, or big O of 1. So when I click this button, this algorithm should get high marks both in the time complexity, the runtime, and in the space being used. So let's see if that's true. Yep. Runtime beats 93%, so it's indeed all the way up here as opposed to big O of n square answers down here. And also, we are fairly decently high up in the memory usage instead of the second algorithm that we created in the previous video that had a memory capacity down here because we were essentially following hint 1, and if you want to check out that story, again, check out the previous video. And with that, we come to the end of this problem where we have optimized the algorithm we've created to get high scores in both the runtime and in the space being used. And big O of n time complexity and a big O of 1 space complexity. Thank you very much for taking the time to watch this video. I hope it was useful in some way to you. And as always, happy coding and have a nice day.